In this lecture, we study metric induced by norm. So basically here we generate more examples of metric spaces. So goal of this lecture is following. So let me write. Goal. So goal of this lecture is following. Generate a class of examples of metric spaces involving vector spaces, over set of all reals equipped with norm, and a vector space equipped with norm. This is known as norm linear space. Okay, so let us begin with the definition of norm. So norm. So let us begin with the definition. So here is the definition. Let X be a vector space over set of all reals. Then a function. So the name of the function is denoted by this, and we read as norm. So this is a function from X to set of all reals. So a function, this is called a norm. This is called a norm if following conditions hold true. So the first condition, this is norm of X, this is greater than or equal to 0 for all X belongs to X with equality. This is equal to 0 if and only if X equal to 0. And this condition is known as positive definiteness. And second condition, for all R in the set of all reals and vectors X belongs to X, we have R times X, norm of this is equal to absolute value of R times norm of X. And the third condition, this is triangle inequality. It says that X plus Y as norm less or equal to norm of X plus norm of Y. And this is called triangle inequality. So basically, if this is your vector space, and suppose this is the vector X, and this is let's say Y, then if you complete the parallelogram, then the diagonal, this is nothing but X plus Y. So length of this side, this is norm Y, and length of this side, this is norm X, and length of this one is equal to the opposite side of the parallelogram. This is equal to norm Y, and length of this diagonal, this is norm X plus Y. And the triangle inequality says that length of this side is less or equal to sum of these two sides, norm X plus norm Y. So this is norm of X plus Y is less or equal to norm X plus norm Y. This is true for all X comma Y belongs to X. Okay. So a function this is called a norm if it satisfies these three conditions. Okay. And a vector space equipped with a norm is called a norm linear space. A vector space X equipped with a norm that is a function from x to r that satisfies these three conditions, okay, is called a norm. Linear space and denoted by a pair x comma norm. So this is norm linear space and x is underlying set, and this is norm on x. So this is also definition. Now we define a metric on x with the help of this norm. So let us let x comma this be a norm linear space. We define D subscript with norm from x Cartesian product with x to r by following x comma y. This is equal to norm of x minus y. Okay. For all x comma y belongs to the Cartesian product of x with itself. And here we prove that this is basically a metric on the vector space x. So before going to the proof, let us consider some examples. Example 1, Rn, comma, this is sub 1. So this is, so where for x equal to x1 and so on up to xn belongs to Rn, norm of x, one norm of x, this is equal to summation xi over I equal to 1 to n. Then this is a norm linear space. So Rn is a vector space over set of all reals of dimension n, and this is a norm on Rn, and this is norm 1. This is defined by here, okay, and so this is a norm, and therefore this pair is a norm linear space. Second example, the underlying set is Rn, and here we define two norm. Okay, so this is defined by summation absolute value or xi square over I equal to 1 to n whole power r, and this is a norm on Rn, and this is called Euclidean norm. On Rn. Now we state as a proposition x comma d sub norm. Okay, this is a metric space. Now we prove this proposition. So basically we show that this function d sub norm satisfies three axioms of distances. So first one is positive definiteness. D sub norm of x comma y. So what is this? This is equal to norm of x minus y by the definition of the function d sub norm. So here is the definition. So d sub norm of x comma y, this is equal to norm of x minus y, and norm of x minus y, this is greater than or equal to 0 by the first condition of the definition of norm. So the norm of x is greater than 0 for every vector in the vector space. Okay, so this is greater than or equal to 0. Now equality holds with the sub norm of x comma y, this is equal to 0 if and only if norm of x minus y, this is equal to 0, and norm of some vector is 0, that is if and only if the vector is 0, that is x minus y, this is equal to 0, and this is if and only if x equal to y. So equality holds if and only if so x equal to y. Therefore this function satisfies positive indefiniteness. And for the second axiom of distances, d sub norm of x comma y, this is equal to norm x minus y. So this is equal to norm minus 1 times y minus x. And by second condition of the definition of norm, so by this condition, what we have, this is equal to absolute value of minus 1 times norm of y minus x, and absolute value of minus 1, that is equal to 1. So this is equal to norm y minus x. And by the definition of d sub norm, what we have, this is equal to d sub norm y comma x. Okay. Therefore, what we have, d sub norm x comma y, this is equal to d sub norm y comma x, and this happens for all x comma y belongs to the vector space x. Now we show triangle inequality. D sub norm x comma y, this is equal to norm of x minus y, and this is equal to norm of x minus z plus z minus y. And by triangle inequality of norm, by this condition, what we have, this is less or equal to norm of x minus z plus norm of z minus y. And what is this? This is equal to d sub norm x comma z plus this is equal to d sub norm y comma z, and this is greater than or equal to, so this is d sub norm x comma y. So triangle inequality holds true. Therefore, we conclude the proposition. Okay, so what we have, so for given norm linear space, we have, so given norm linear space, we have a metric space x comma d sub norm, and where this metric is induced by the norm, okay, on the vector space. For examples, so for example, already we have seen that this is norm linear space, and this is also norm linear space. So this norm linear space induced vector space. Okay, so here we would like to study some special norm linear space, some special non-linear space. So we would like to study some special non-linear space, namely LP spaces. So now we define what is LP. So here is the definition. Let's say P lies between 1 and infinity. So that is P belongs to 1, comma infinity, this interval. Now we define LP. So this is the underlying set. This is equal to set of all real sequences x equal to sequence xn, that n belongs to set of all naturals, such that x, so this is real sequence, xn belongs to R for every n belongs to set of all naturals, and summation absolute value of xn power p over n equal to 1 to infinity. So this is less than infinity. So this infinite sum is has a limit. Okay, so this is which is finite sum, and so this is the definition of the set LP. Okay, for P belongs to this interval close 1 open infinity, and now for P equal to infinity we define LP. So LPP equal to infinity, so this is equal to L infinity. So this is the set of all bounded real sequences. So x equal to xn, n belongs to set of all naturals. So this is sequence in reals, xn belongs to R for all n belongs to C for all belongs to set of all naturals, such that this is bounded, that is supremum of xn, absolute value of this. Okay, n belongs to set of all over n belongs to set of all naturals. This is finite. So this is set of all real bounded sequences. Now so these are the underlying sets. Now we define addition and scalar multiplication in LP. So addition for x equal to sequence xn and y equal to sequence real sequence yn belongs to LP. We define x plus y, this is the sequence xn plus yn, and belongs to set of all naturals. And scalar multiplication for x equal to sequence xn and r belongs to R, we define Rx. This is equal to the sequence R times xn over n belongs to set of all natural numbers. Okay. Now we show that. So our claim is LP is closed under addition and scalar multiplication. So basically we have to show that for x comma y belongs to LP, we have x plus y belongs to LP, and second, R belongs to set of all reals and x belongs to LP implies Rx belongs to LP. And okay, so in a moment we will do this, and now we define another notion. Definition. So we define functions. So norm sub p. This is from LP to set of all reals. by following. So we have two cases for if P belongs to the interval 1, infinity, then this is defined by, so then, and x equal to the sequence xn belongs to LP. So we define norm x of P norm of x, this is equal to x n absolute value of this power P, then summation over n equal to 1 to infinity, then whole power 1 over P. And for P equal to infinity and x belongs to L infinity, so x is equal to sequence xn, this is real bounded sequence. So we define, so this is equal to infinity norm of x, this is equal to supreme norm of absolute value of xn, where xn are the terms of the sequence x. So the supremum is taken over n belongs to set of all natural numbers. Okay, and our goal is to show that LP, this function, these are non-linear space. So basically, we have to show that LP is a vector space with addition defined here and scalar multiplication defined by here. Okay, so first of all, we have to show that LP is a vector space, and then we have to show that this is a norm on LP for every P. For every P belongs to the closed interval 1, infinity, and P equal to infinity. Okay. So next time we prove this. Okay, so now stop here.